Hi, we're going to talk about polyprotic acids. So let's break this down and it will make good sense for you. Poly means many, protic means proton. So it means that these are going to be acids that can donate more than one hydrogen, more than one proton. So monoprotic, proton, this would be something that only has one hydrogen, and that's going to be a lot of our acids, like hydrochloric acid. So that would be one hydrogen. Now a diprotic acid would be able to donate 2 hydrogens, like sulfuric acid. Triprotic acid can donate 3 hydrogens, like phosphoric acid. So notice the diprotic and the triprotic, those are going to be our polyprotic, that they can donate more than 1 hydrogen. Now, this is really important. The acids donate hydrogens one at a time. So they donate 1 hydrogen in a reaction, and then a completely separate reaction, they're going to donate the second proton, and then the third proton would be its own third reaction. So I have used phosphoric acid. I want to show you how we write. The deprotonation is what it's called when we lose a hydrogen, when the acid donates a hydrogen. The deprotonation, so we're going to have 3 reactions because I've got 3 deprotonations. We're going to lose 3 hydrogens. So you start with this phosphoric acid, add it to water, so it's just an acid plus water. Remember, phosphoric is not one of our strong acids, it's a weak acid, so it's only going to partially react. It will have an ionization constant that's less than 1. So phosphoric acid plus water is going to produce, okay, now check this out. I have H3PO4, it loses 1 hydrogen, donates 1 hydrogen, so now that's H2PO4. Now just a reminder, when you lose that hydrogen, that positive, you're going to have a negative. There's going to be a net negative charge, 1 more negative because we lost the positive. So for every hydrogen you lose, you're going to add a negative. So H2PO4, this is called dihydrogen phosphate, plus, all right, the water accepted that hydrogen, and so it's going to become our, that's going to become the hydronium. Now, just a little reminder on labeling, I want you to see something. We're going to pull in something that you learned from a previous video. We're going to have acid, base. The acid always produces the conjugate base, base produces the conjugate acid. Okay, hold on to that. Now, we still have 2 hydrogens to lose. So I want you to picture in the solution, you have that phosphoric acid reacts with water, okay, makes these 2 products. Now this dihydrogen phosphate, it can react with water, it can interact with water. So you take this product and it now becomes the reactant. So this dihydrogen phosphate is going to react with water. Notice I don't write it reacting with hydronium. It's not going, this right here is going to do its own reaction to donate a hydrogen to the water. So you write a second separate reaction. So again, this product is now going to do its own reaction with water. I want to mention too, this is going to have its own Ka. It will have, that will have its own ionization constant. The ratio when it reaches beautiful equilibrium of what the concentration of products are over reactants. Okay, so here, I now have my dihydrogen phosphate, add it to water. This is going to donate a hydrogen. So it donates the hydrogen to the water, and oh, look what happens now. I had 2 hydrogens here. Now I only have 1. It lost another hydrogen, donated another hydrogen. And so because it's lost a total of 2 hydrogens, it's now a -2. We lost 2 positive charges, so now it has a -2. And the hydrogen goes to the water, that produces hydronium. This has its own Ka as well. It's going to have its own equilibrium constant. Now, I want to do the labeling again and point something out. So this is going to be our acid, is going to donate the base, and then we have our conjugate base, conjugate acid. Here is what I wanted to pull out. Notice the dihydrogen phosphate is the conjugate base right there, and down here is the acid. Do you remember what it's called when there's a species that can act as both an acid and a base? It's amphoteric, like amphibian, ambidextrous. So this, I'm just going to pull this out as a little side note. PO4 minus, this is going to be amphoteric. Now, it's an amphoteric species, meaning it can act like both an acid and a base. On our polyprotic acids, you will always have at least one species. If it's diprotic, you'll have one species that's amphoteric, and if it's triprotic, you'll have two species that are going to be amphoteric, because it becomes one species conjugate base, and then it's going to act like the other species acid right here when it reacts with the water. Okay, just wanted to tie that in for you. All right, so our products now, hydronium and this is called hydrogen phosphate. Okay, we still have one more hydrogen that can donate, one more hydrogen that can be given away as an acid. So we're going to come down here, you bring this product down here because that hydrogen phosphate is going to do its own reaction to donate the hydrogen to water. So we write a completely separate reaction. Hydrogen phosphate plus water, so this is going to donate, look at this, loses the hydrogen, what's left over? Phosphate ion, no hydrogens. We're finally done, it's donated all 3 hydrogens. Notice we lost 3 hydrogens, so you have that -3. Lost those 3 positives, so now it's a -3 charge, plus the hydronium. And this also has its own Ka value. I do want to point out, looking at these two, can you see the next amphoteric species? What acts like both an acid and a base? Here, the hydrogen phosphate is a conjugate base, but down here is going to be the acid. So your second amphoteric species is going to be the hydrogen phosphate right there. Okay, now there are 3 really important applications, and I've written them down here. I also have a video actually doing the math and showing you this. So here are the 3 applications. When you have a polyprotic acid and you're asked to find the pH, I'm going to give you the quick, dirty way to do this. You only do the ice table for Ka1, for this one right here. And here's the reason why. If you were to look up the Ka values of each of these, Ka1, Ka2, Ka3, Ka1 is always significantly larger than the Ka2, and Ka2 is larger than Ka3. So here's what happens. All 3 of these reactions produce hydronium. So even if I did the ice tables for my Ka2, my Ka3, the hydronium that's produced is so small that when I go back and add the hydronium that's produced here to this hydronium, it doesn't change it. For sig figs, it doesn't change it. This hydronium is always going to be significantly larger than the amount of hydronium produced here and here. So to get your pH, you do 1 ice table, and it's always off of Ka1. Okay, so that's the first really big thing you need to know. Now, the second takeaway that's very, very interesting is when you get to your very last equation, the final conjugate base, so in this case it's going to be the phosphate ion, its concentration is going to equal the Ka3. It'll equal the Ka3. And I'll show you that in the next video. It will just say polyprotic acid practice. You can actually see the calculation as to why that final conjugate base or conjugate acid, whatever that final product is, that is the same concentration. Its concentration equals the Ka3, that last equilibrium constant. So those are your big takeaways. Do the ice table for the first one using Ka1. You'll know that these Ka values decrease with each successive deprotonation, successive loss of hydrogen. And if you have to find the final concentration of the last product, it equals the concentration of the Ka3. Okay, well there you have it, polyprotic acids. To find the video to practice, it's under the acid-base equilibrium playlist. All right, thanks, have a great day.